Hi again, everybody. Today we are going to look at, of course, gradient of a graph. And probably would have heard the name before, probably not. Gradient is actually known as, of course, or is dubbed the steepness of a slope. Now, you think about the steepness of a slope, and of course, the term slope is used quite loosely both in mathematics and physics. Because if we were to take a very simple diagram, now of course, I'm just going on to just analyzing what we need to know, right? So you have two slopes, so two hills. I'm going to call one A and the other B. This is A, sorry about that. And of course, this is B. And of course, the one that is harder to climb will be the steeper one. So between these two, if you look closely, the one that is harder to climb is one that is closer to the vertical axis. Now, if you're not sure what the vertical axis is, we'll get down to it. So this one is steeper, and of course, this one, part B, is less steep. Why? Well, it's going to be harder to climb, yes. I'm going to just write harder to climb for now. Because the thing about gradient is that it appears in many different subjects. Mathematics, physics, geography, when you're doing your math reading, etc. And one of the things that we need to know is how to find gradient. But before we get down to how to find gradient, let's break down what gradient truly is. And of course, I'm just going to do a sketch of a graph so that we have a better understanding of it. Just going to draw my line. So this is our gradient. This is our slope that we are looking at. And of course, as I said, sometimes the word slope is thrown around to show how steep something is. Yes, it's also thrown around to represent what gradient is. So many questions ask you to find the slope, meaning find the gradient. All right, so what do we know about these two uh, axes? We know we call one the y-axis, which we know is our vertical axis. So I'm going to write vertical here. Vertical plane or vertical axis. And the other one is our x-axis, also known as the horizontal axis. Now, or horizontal plane. Now, another way it's used, a lot of times in map reading and geography, if you are going higher vertically, it's called the rise. If you're going across, it's called run. But let's get down to it. If this white line represents a vector, for example, I can get from the origin to the end here in two ways. I can travel along that straight line, or I can travel horizontally some known distance, followed by upwards some known distance, completing therefore a right angle triangle. So I have two ways to look at it. But if I didn't even want to put vectors in, just take my arrows off. Let's make it quite simple. I can actually take, therefore, what is called the horizontal distance and our vertical distance. Our horizontal distance, if you are moving along a horizontal surface, for example, you're running a race along a horizontal surface, we say that we are running along that surface. But if a balloon is going up into the atmosphere, for example, if you have a balloon going into the atmosphere upwards, we say the balloon is rising. So we say a vertical movement is called a rise, of course, upwards, right? So in essence, just to relate what gradient really is, and of course to bring this full circle, gradient can also be known as the ratio of rise to run. Very useful if you have to find gradient, as I said in geography. This is our starting formula for gradient. This is our basics behind it. Now, we can bring a mathematical concept or understanding into it, which I'm about to do. But I'm just showing you, as opposed to just traveling along a white line, which is our vector, we can travel horizontally and across. The ratio of the vertical movement or distance traveled to the horizontal distance traveled, which is rise over run, gives us therefore our gradient. But let's get down to the mathematics behind it. So let's consider that we have a graph. It's now as a sketch, just to begin with. And to find how to calculate gradient, well, we can use this method for pretty much any calculation with regard to gradient. We already established that gradient refers to, I'm just going to put gradient. Now, in mathematics, that symbol is common M. is equal to our rise over run. This comes from the equation of a straight line, of course. But rise over run, let's get down to where this rise really, what takes place. To find gradient, you select 2 points on your line. It can be any 2 points, because if it's a straight line, it would mean that any 2 points would give us the same gradient. I could select them close by, further apart. Physics-wise, which I'll do in another lesson, we take them further apart to avoid errors. But I'm just going to take 2 points on our line. So 2 points, I'm going to take this point here, and I'm going to take this point up here. And because it's a sketch, I'm just going to relate what these points represent. So our first x1, first x value, first y value, giving us our first coordinate. So I'm going to call this my coordinate x1, y1. Our second point is going to be taken, of course, from another x point, x2, y2, or an x coordinate that is. And of course, this is, I'm going to label it as x2, y2. Very simply put, looking at our equation, of course, looking at our graph, sorry, we can actually see that we can get rise over run right here. We can calculate our gradient. We have a run which is along the vertical axis. What is run here? It is a change in our vertical axis. Of course, a triangle represents delta, capital Delta, Greek alphabet. That means change in y. Our run, I'm going to put run here, is change in x. But let's further break that down. Our change in y is known as a difference in y. So we can take our, I'm going to take a bigger value in this case, y2 minus y1, subtract y1. This is our run, our change in our vertical axis. So our rise over run mathematically becomes change in y over change in x, representing the axes that they come from. Now, in that case, therefore, run will therefore be x2 minus x1. The larger of the two values minus the smaller one. We're going to realize that it wouldn't matter which one you subtract. It is just for us to understand that our equations should line up. So what does gradient therefore become? Our gradient, therefore, to calculate gradient, our change in y from our substitution becomes y2 subtract, of course, y1 over x2 subtract, of course, our x1 value. This is pretty much a standard equation that I'm going to do some examples now to show you. Will work for pretty much any equation involving finding the gradient of any straight line. Right? Let's do some examples to see. Okay, so we begin with a very simple graph. Of course, I took the liberty of using a graph already drawn. And of course, our example, let's just be able to first be able to find gradient is using method I mentioned. Now, this is a graph of those of you who do math, and of course, everybody should have done math. But this is a graph of y is equal to x. I wouldn't get into the equations right now. I'm just going to take 2 points from this graph, from this line that is, more specifically. I'm going to take the one up here, and I'm going to take the origin. All right, we are going to have examples where we wouldn't take the origin. And once again, I'm going to label my points. So the origin is 0, of course, 0. And this is our x1, y1 point. I'm going to label it x1, comma, y1. All right. Our point at the very top, it's 4, 4. And of course, as I said, this graph is a y is equal to x. The equation of the graph is y is equal to x. So the same points lie for both x and y axis, on the y axis. This is my x2, y2 graph. And to make sure we can see it, this will give us, therefore, our rise, as we said, our change in y. And horizontally, this will give us our run, our change in x. So let's get down to it. How do we find gradient of this line? The formula is y2 minus y1 over x2 minus x1. It is very important to label these points so that you can see them. And of course, this is if you prefer to write, of course, change in y over change in x so that you can see it, or even rise over run. Now, all of this means the same thing. I'm going to substitute now my y2 point. It really helps if you can label your points next to your coordinates. So 4 minus, of course, our y1 value is 0 as taken from the graph, divided by 4, which is again our x2. Take a simple example, minus 0 once again as our x1 coordinate, well, point. We will end up getting 4 minus 0 is 4, 4 take away 0 is 4 as well. 4 divided, now please don't put 0, this is actually 1. So our gradient therefore is 1. Steepness is 1 in this case. Alright, let's take another example. Alright, so in looking at number 2, our example number 2, let's do the same. Alright, so again, once again, let's select 2 points on this line. And I'll explain why at the end, why we take it on the line. For now, I'm going to take 2 points that are pretty much straightforward. Now this point is actually dotted, right? So it's made possible for us to use. And of course, in doing so, let me just switch my marker. I'm going to first label my point. This is my x1, y1 point. Ah, I guess that looks like that. And of course, this point is given as 0, 1. I'm going to take my point up here, second point, which is of course my x2, y2 point. And once again, this point is, if I read it off of my graph or my grid, it's 2 from the horizontal axis, comma, 5. Alright, so once again, we have 2 values. I'm going to relate it here. Our gradient, therefore, is going to be our change in y, as we said, over change in x. And we also mentioned it is y2 minus y1 for our change in y, over x2 minus x1. And of course, this reason why it's change in y over change in x, because of course the angle given, if you were to bring trigonometry into it, would be the same at any point in the slope or any straight line further. Well, if the straight line continues on to what we say infinity, or any large enough value for us to note. So our y2 is going to be 5 by substitution. Our y1 value is 1. It's nice to read off from your graph and not have to fish it. Now, common mistake a lot of students make is that they don't label the points, those points x1, y1, y2, x2, y2, sorry. And of course, they substitute in the wrong place. And that's the last thing you want. All right, x2 would be 2 minus 0, our x1 value, that is x1. What we will get, it's 5 minus 1, which is 4 over 2. So our gradient is 2. Now, what I didn't point out, and what I'm going to point out now, is both our examples, we got our answers to be positive. It means, therefore, our gradient is a positive gradient. Goes as a diagonal from left to right, but I'm going to break it out at the very end. We're going to meet, therefore, and I'm going to take a little note of it. This is a positive. Let me write that word out. So this is a positive gradient. And of course, just to make it simple, it goes that way from left to right. But I'm going to show you an example of where we get another type of gradient, which is not going to be positive. We have at least 4 types to pay attention to, or 4 main types to pay attention to. So here we have another example that we can look at, example number 3. And of course, if you look, the slope is quite different from the previous 2 examples that we had done. We had gotten 2 positive gradient examples. Let's see, applying the same formula here, what we're going to get. Now, I'm going to label, as we did before, our 2 points. And I'm going to take any 2 points on the line, all right? So I'm going to take this one point that is easy for us to have right here. I'm going to take this one right here. Now, I'm taking 2 points as close together as we can. it's a straight line, so you will get the same values. But I want you to note that for physics students, that is, we take points as further away as possible, far away as possible on our line, forming a large triangle, so that we can eliminate any possible errors. So you might be wondering, where do I take my x1 and where do I take my y1 values? Well, in this case, to be honest, it does not matter once you label your points correctly. So here it is. I'm going to show you where we get this rise over run. All right, this is where we take our first. I'm going to take this first value here as this. I'm going to call this value x1, y1, given my point. Therefore, this point up here called our x1 comma y1 point. And this is my x2 value if I were to continue onwards here. And this is my y2 value. As I said, it would not matter. You can reverse this, all right? Now, that being said, this point will now be our x2, comma y2 coordinate or point. Let's label. So our x1, y1 point. X1 coming straight down. You look at the point first of all, you go down to the axes, with horizontal, then vertical to create a coordinate, all right? And of course, our first point, it's 1. Oh, that's 2, right? That's 2, right? This point, x value is 1. Our y value is 3. We have our first coordinate, x1, y1. x2 would be 2, as read off from the graph itself. And y2 would be 1. Now, in any instance, somebody could label this quite differently and we will attain the same answer. I could have labeled this point at the very below here, which is what I chose to be x2, y2. Someone else would have said, okay, I'm going to call this x1, y1, and reverse the orders, of course, and call this one x2, y2. At that point, I'm going to be very honest, it does not matter. All right, so how do we find our gradient from this? Same formula. We said, remember, this was our change in x, and of course, our difference or change in y from our graph. Same concept, the same concept applies. Our change in y, which is our rise, change in x, run. So I'm going to put my formula y2 minus y1 from our graph itself over x2 minus x1. Let's see, straight from the graph. I'm going to substitute now. y2 is 1. Please substitute correctly. Stop and check. Minus y1 is 3 over x2 is 2 right here. x1 is the value of 1. Let's break this down. Numerator first, 1 minus 3, 1 take away 3. Okay, now people tend to get confused with this. Think of it as terms of money or monetary value. You have $1. You owe someone. I always say if you owe someone, negative values, if you owe, or if there's a difference in values that you have for somebody. So you owe or you don't have, you borrow. So you owe or borrow money, it's negative. All right, so let's say you have $1, but you borrow 3, or you owe someone $3. You have $1, you pay them $1, you borrow 3. You still have a balance. And if you still owe or borrow anything, it's still minus. All right, if you're not sure about the negative sides. So you get minus 2. You still owe $2 now, if you want to look at it in terms of a monetary value. And of course, in taking away regular values, a bigger minus a smaller value will give us, of course, smaller value. So 2 minus 1 is 1. Well, now, any number divided by 1 is itself. So you're going to get a minus 2. You might say, well, my God, how did we get a negative? This negative value plays a big role. It just tells us that a slope running as such, this direction basically, gives us a negative gradient. We have just been introduced to our different type of slope, second type of slope, that is negative gradient. All right, so let's do one more example with our negative gradient, and then we'll go into the 2 last types before we summarize. All right, so here we have our 4th example of gradient, and not just our 4th example, our second negative gradient example. Now, in doing this, and of course, we're going to go along the same method. You might say, oh my goodness, this is negative, but if you're not going to use the same method as we did before, I'm going to call this my first 1 point. To make it very simple, I'm going to use this point as cutting the, of course, y-axis or vertical axis. So the point that I take to the very top, I'm going to call it x1, y1 once again, comma, right? And the one to the bottom here is going to be x2, comma, y2. Let's read them off and make sure we understand it. Now, our first point to the very top of my graph, keep in mind this is a different shape of the slope. We have met slopes that go positive, which is in the opposite direction. I'm going to read them off first. And of course, this value is, it's your x value first, of course, followed by your y value. Our x value here, it's minus 2. Our y value across to cut our y-axis, it's 1. All right. Similarly, our x2, y2 points, it is, of course, we don't have as an x value. You notice it's running along the y-axis. I'm sorry, it's cutting here where the origin exists. This is running along the point where x is equal to 0 with minus 1. It's like a number line. This is a negative section of a number line, for example, our x-axis. I always say that. So this is, of course, we have no x value. However, we do have a y value, which where the graph is cutting. Which axis? The vertical axis. Our vertical axis is the y-axis, of course. So this is minus 3. We have two coordinates again. And let's see if we can understand once again our rise over run concept. Now this is our run horizontally, our change in x. This is rise, and you might say it's not rising, it's actually dipping, it's still along the vertical axis. And this is why we have a negative gradient. And this is, of course, change in y. So let's analyze, shall we? So we're going to write, of course, what we have been writing all along for previous examples. Gradient is change in y over change in x, rise over run again. And you might say this is not rising. Of course, it's going downwards. But this is the reason why we're going to get a negative value. So change in y, again, I'm going to write my formula y2 minus y1 over x2 minus x1. And to be quite fair, some people like to shade that triangle that they're forming. You don't have to. So you can still see it's a triangle that we use, and of course, it's a right angle triangle. So y2, of course, straight from our graph is going to be minus 3. And again, it's based on what you call y2. But keep in mind that your y value, your same coordinate, and an important thing to remember here is that these should line up. Look at our x, this is a coordinate over another coordinate. All right, so y, this is 3, of course, minus 1 over x2, which is 0, minus, now keep in mind, our x value, x1 value, it is already minus. So I'm going to put it in brackets, minus, just so you can see it. This is already minus from our graph. Now, some people find it very useful to do something like this. If you don't want to label from your graph, which I will always recommend, they label their values so they can see it. x1, y1, it's minus 2, 1. At least close to where they're going to write their gradient. x2, y2, as we said, is going to be 0, minus 3. Right, so when you substitute, you can see everything in front of you. That's just another method that you can use. Another way you can see all your values without making any errors, or minimize your errors, in fact. So minus 3, minus 4. Remember what I said about the minus values. If you're not sure, if you owe someone $3 and you borrow another dollar, you owe them $4. Once you're owing, it's negative. All right, divided by. Now, right away here, these are two negative signs, and we know this. Negative and a negative, we say it becomes positive. So 0 plus 2, it's going to be 2. Minus 4 divided by 2 is the same as writing minus 4 over 2. Let's simplify this fraction. 4 over 2 is 2. Our answer will be negative. Negative 2, for example, gives us a negative gradient, and it tells us that the slope, therefore, is going in this direction. That's all we're saying. All right. In terms of physics, this represents something with regard to acceleration and deceleration, but when we reach that point, I'll reiterate this point. So this is our second type of gradient we are going to meet. Our positive goes in the opposite direction to what I have as my slope here. Negative goes diagonally downwards, for example, like this. Right, from the left going to the right downwards. Let's check our third type, or in any order actually, I should say our third type of gradient. Okay, so here we have another example where we can also find gradient, and you might say, well, my goodness, it's a horizontal line. Well, let's still take 2 points on this line because a horizontal line gives us something very special with gradient. A horizontal line, in taking these 2 points, of course, I'm going to take my first point as the one that we can see. And any point along this horizontal line, I'm going to call my first point, therefore, x1, y1, everything we've been just doing, and x2, y2. And of course, a horizontal line, in fact, you can look at it and tell. We don't have a rise. So we don't have the rise component of our gradient. So let's see, can we still find gradient? Let's read off this first value. It is 0. We don't have an, as we said, we have our x value here is 0. Our y value, it's actually cutting, this line is cutting our y-axis at 5. So we have a y value of 5. Let's see what's going on here. Our x value is considered to be 3. Our y value is considered to be 5. So, do we have a slope in fact? Well, no we don't. But I'm going to still show you, in using our gradient formula, what happens in this case. Gradient, we said. Now we have a change in the x value. So I'm going to note here. We do have a change in our x value. Notice the x value goes from 0 to 3. However, the y value does not change. So I'm going to write still our change in y over change in x. Now I'm still going to calculate so you can see it. Right away, some of you will actually see that if we have no change in y, something happens to our numerator. But let's write our formula. y2 minus y1 over x2 minus x1. Our y2 will be 5. y1 is also 5. We would have iterated that before. There's no change, hence the values being the same, are the same. Our x2 value is 3. x1 is 0 right away, and of course you'd have spotted this in the very beginning. Same number minus, of course, take away or subtract itself is going to give us 0. Over would not, what our denominator is. 3 minus 0 is 3, but if our numerator is 0, our gradient or our answer becomes 0 for that fraction. What does this mean? Well, this gives us our first case that we should pay attention to. We would need to calculate this if you see a horizontal line. A horizontal line has what is called gradient, which is equal to 0. So I'm going to put gradient, which is 0. So in essence, whenever you see a horizontal line, why is that so? Because there is no change in our y value. The object is not moving upwards at any point in time. It's only going along a horizontal plane. So there's no vertical change or rise, as we say. So there's no rise in this line. I'm going to put a little note. There is no rise, as we say, or no change in the vertical component or vertical axis or movement, even movement, right, in the vertical. So this is just one thing that we should note. A horizontal line has a gradient which is 0. Let's look at a vertical line. Okay, so once again, we're going to look at our yet another case of a line, and in this case, of course, it's a vertical line. So, and you should look at, most people say, oh, okay, a vertical line also 0 gradient. Well, let's take a look, because this is another common misconception we can actually clear up right here. So I'm going to take my 2 points once again. All right, now I'll get down to the scale reading in a bit. But please note, I'm going to take my first point, the higher, okay, my first point, which is the bottom. I'm going to call this x1, comma, y1. And the one on top is going to be x2, y2. And I'm going to label. My first point down here, my x1, y1, it is, now if you look at the scale of that grid, you have 0 to 5, and you check you have 1, 2, 3, 4, 5 lines, which means one line represents, of course, one little line represents 1 unit. 1, 2, 3, this is my third value. So x1 is 3. Y1, we don't have a y1 value. Why? No pun intended. But there's no y value because it's actually lines the x-axis. Any point taken along the x-axis has no y value. All right? And it goes on to the equation of a line, which I'll get to in another class as well. So our x2 value, notice again, the x2 value is not changing. it's still, sorry, it's still 3. My mistake. It is still going to be 3, but our y2 value changes. It becomes 15. So we do have a rise involved here. So we do have a rise, which we have our change in y, but there's no change in our x value. So I'm going to put no change in x. All right, so it's also written as, you can put it as no change, no, sorry. Change in x does not exist. All right, so let's get down to it, shall we? All right, so what do we look at here? Once again, I'm going to write my gradient formula. Just to show you, you probably would have already spotted it, but this is just to clear up the misconceptions that people may have. Change in y over change in x, no problem. Change in y using our formula, it's y2 minus y1 over x2 minus x1. Our y2 value, I'm going to substitute so you can see it. It's 15 minus y1, 0 over x2, which is 3. And we should already know there's no change in x. So a change in x, therefore, at this point, we should know that that is 0. No change in x is going to be 0. All right, so no change in x means change in x is going to be 0. So it's 3 minus 3. Now what do we get? We're going to have a y value. 15 minus 0 is 15. Well, what was going on to our x value? This is going to become 0. And most people think, this is 0. Well, that's not 0. And of course, I'm going to take it off so we wouldn't learn the wrong thing. What we need to pay attention to, any number divided by 0. If you do it on a calculator, for example, type in any number you want, 10, 5, 15, etc. Divided by 0, you're going to get error on your calculator. That error represents what is called an undefined value. Undefined solution. So it means that we don't have a solution, there's no answer. The graph is therefore tending to be say to the vertical. It also means to us, we just shorten that to call it. Most people know the symbol. No, it's not eyes, it's actually infinity. Number is so large, it's considered to be infinitely large. All right, so this is just a point to note. What does that mean to us? That means to us that a vertical line has a gradient that is undefined, which I'm going to just put as a symbol infinity. All right, now please note infinity is not an actual value, it's a term. So it gives us a value of something being so large that you cannot compute. So let's summarize what we have just learned. So let's look at a little summary, a short summary, or summary I should say, of what we are going to look at. And the summary is that we found that gradient can be taken from any graph, of course. Now, just to remind yourself, a coordinate is written as x1, comma y1, or xy, the x value followed by the y. X is your vertical axis, the y, x, sorry, is your horizontal axis, y is your vertical axis. Now, what do we need to know about this is that your gradient is equal to what we call our rise over run. And always remember, if it's a rise, you're going vertically followed by horizontally, or it's a ratio of the vertical to the horizontal axis. Our vertical axis we call our y-axis. Horizontal, we call it the x-axis, hence this term. Now, if you select 2 points, any 2 points on that line, that straight line, I'm saying line, and not graph, because I will get to best fit in a little bit. Our change in our y, therefore, becomes difference in our y values. Of course, however you label, difference in the y values will be our y2 when you select your 2 points, x1, y1, and x2, y2. It would mean that the difference in values obtained from those 2 points selected from your line. And it will therefore mean our difference in y will be y2 minus, or take away y1, x2 over x2 minus x1. This is our gradient formula. In mathematics, gradient is known as common. That symbol is given as common m. Physics, it represents whatever you are trying to measure. Now, in essence, let's summarize the different types of gradients that we can possibly get. Our positive gradient. So whatever answer we get for our slope going along a diagonal going right, this is our positive gradient. So we're always going to get a positive value for gradient. Negative gradient, once the slope is in this general shape, we get a negative value. Zero gradient, this is of course a horizontal line. A horizontal line gives us a gradient which is 0. Alright, so, and of course a vertical line gives us gives us a gradient which is what we say undefined. Another way to state undefined, we say is infinitely large. So these are just a few points to remember with regard to finding gradient. So we can find a computable value, for example, for gradient. Of course, these are quite relative to motion, graphs. These are relative to finding, well, application in map reading and reading a map, for example, and you want to find out how high a mountain or a hill is. You use the same concept of gradient. And these are our four main types. 1, 2, 3, 4 that we would have covered in this class. All right, thank you very much. And if you do have questions, please feel free to comment below or ask away. Thank you.